Okay, let's continue this section. Okay, the next one, you see, we already discussed the behavior near a zero. Let's talk about other behavior. The behavior at infinity is called the end behavior. The end behavior. What is the end behavior? The behavior of the graph of a function for large values of x, either positive or negative, either positive or negative. Large positive to the right, you move to the right. Large negative, you move to the left. Okay, either positive or negative is called its end behavior. Okay, so you're talking about the behavior when the graph is on the right side, on the right end part and the left end part. And we are not going to discuss or give the detailed description, but we are going to just introduce the theorem directly. Behavior. And the behavior theorem says for large values of x, either positive or negative, the graph of the polynomial function. What is a polynomial function? Fx is equal to an x to n, an minus 1, x to n minus 1, a1, a0, a1x plus a0. This function resembles the graph of the power function. What power function? Y equal to a sub n x to n. So you just select the leading power. So the end behavior theorem just tells us if you have a very large x, either negative or positive, when you have a very complex polynomial, you only consider the first term. That's enough. The leading term is enough. If the leading term is a very, very large number, then it makes the whole polynomial function a very large number. If the leading term is a very, very negatively large number, then the whole polynomial will be negatively large. Okay? So that's what it means. So for example, if we have this function, negative 2x cubed plus 5x squared plus 5x and minus 4. Okay, so this is a very complex polynomial function. How do we know what the behavior it has at the end for a large number? We just check the negative 2x cubed. Negative 2x cubed has a graph more or less like this. X cubed has graph from first quadrant to the third quadrant, but with the negative sign you flip it. Negative 2x, you flip it, so it's more or less like this. And when x is very, very large, so it's like it's here. When x is negatively large, it's here. So only we pick up these two parts. This is a y equal to negative 2x cubed. We pick up these two parts, we will see that our function fx, this polynomial, when it is very negative or very positively large, negative large, at these two end parts, the graph will be more or less like this. It will go to the positive infinity here, negative infinity here. So, and between them, of course, it's more complex since when x is small, the rest of the term matters. But when x is huge, the rest of the terms do not matter. Only the first term matters. Okay, so that's what it means. Resembles. You just get this piece and get this piece. Okay. Okay. Now let's see the example. The example is the following. Example. Which of the graphs could be the graph of fx is equal to x to 4, 5x cubed, 5x squared, minus 5x and minus 6. Okay, we have 4 graphs. So first graph is like this. Okay, this is the first one. And second graph is like this. And third graph is like this. And the fourth graph is like this. Okay, so which graph could be, okay? Which of the graphs could be this? Then let's check. First of all, by the end behavior theorem, when x is huge, positively or negatively, then you just ignore the rest of the part, you only check x to 4, okay? So it's A, B, C, D. Okay, so we first check the function y equal to x to 4. Y equal to x to 4 is like this. So at the two ends, the graph of this function should be like this, up, up. But this one is not correct. D is not possible. Okay, so by end behavior theorem. And behavior theorem. Okay, that's the first condition. By this and behavior theorem, we remove this D. And second, let's check. Let's check the y-intercept. Y-intercept f0. F0, 0, 0, 0, 0, negative 6. Okay, y-intercept f0, negative 6. Negative 6 below the x-axis. So here's below, here's below, here's above. A is not possible. Okay, A is not possible. Now what's next? The turning point. Turning points theorem. Turning point theorem. This is degree 4. Degree 4. F can have at most 3 turning points. Okay, degree 4, then it can have at most 3 turning points. In this one, 1, 2, 3. Here, 1, 2, 3, 4, 5. So C is not possible. So we remove A, C, D. So B is the only possible choice. So B is correct. Okay, B is the correct one. So you see here, this problem is very comprehensive. You have to understand all the concepts we have discussed and try to put them together and get the result. Okay, so on page 332, there is a summary, a boxed summary, blue box. And this summary is very, very important. Actually, it just covers what we just discussed. The degree, graph, maximum number of turning points, even multiplicity, odd multiplicity, between the zero, the graph is below or above x-axis, and behaviors. So check these summaries and memorize them. That's very, very important. Okay. With this in mind, let's analyze the graph of a polynomial function. The fourth part. Analyze the graph of a polynomial function. How to analyze it, okay? Example. We have a function fx equal to 2x plus 1 times x minus 3 squared. 2x and 1, x minus 3 squared. This one has degree 1, but squared has degree 2. Here you have degree 1. Degree 1 times degree 2 is degree 3. So first, the degree is 3. Okay? Then what is the leading term? What is the leading term of this polynomial? To get the leading term, you just use the leading term times leading term times the leading term. Okay? So check here. It's the function is actually like this. So you're going to just use leading term times leading term times the leading term. Then the leading term is 2x times x times x is 2x cubed. And this means by the graph and the graph, and the behavior theorem, the graph of f behaves like y equal to 2x cubed for large values of ops value of x. If you don't want to say negatively or positively, you just put ops value. Okay, so this is an and behavior theorem. It's an and behavior theorem. We're going to understand this. Okay, this is a step 1. You have degree, you find the leading term, and you get the corresponding and behavior theorem. Step 2. Let's talk about the intercept. Y-intercept, f0. F0, so it's 1 times negative 3 squared. 2 times 0 is 0, plus 1 is 1, so 1. X minus, 0 minus 3 is negative 3 squared, is 9. So y-intercept is 9. X-intercept. X-intercepts fx equal to 0. 2x plus 1, x minus 3 squared. So first term is 0, so you get x equal to negative 1/2. 2x plus 1 is equal to 0. X is negative 1/2 of multiplicity x minus 3 is 0. X is 3 of multiplicity 2. This is 2. Okay, so this is multiplicity 1, multiplicity 2. And after you get the multiplicity, you can see that the graph touches x-axis at 3, crosses the x-axis at -1/2, because odd multiplicity cross, even multiplicity touch. And step 4, you have a degree 3 polynomial. There are at most, we never say it is equal to 2, we just say it has at most 2 turning points. At most 2 turning points. Okay. And step 5, behavior near zeros. We have 2 zeros, right? -1/2 and 3. Near x equal to -1/2. -1/2 comes from 2x plus 1. You keep this 2x plus 1. You replace x by -1/2 in other terms. So it's a -1/2 minus 3 and square. What this is? It's 2x plus 1. -1/2 minus 3 is the -7/2. It's 49/4. Okay, so -1/2 minus 3 is -7/2. -7/2 square, 7 square is 49, 2 square is 4. And you distribute into the parentheses, 2 times it is 49/2 times x, and 1 times it is 49/4. Well, not only I make mistake. I think in the textbook they also make a mistake. Check on page 333. When they do the computation near -1/2, I copy it here. They had a approximation 2x plus 1 times the pink -1/2. They put plus 3 and then squared. Right above it, it's a minus 3. It should x is -1/2, so it's a -1/2 minus 3, not plus. This is minus. Oh, very good. Okay, I'm not the only person make mistake. Anyway, this is a straight line. So close to -1/2, you have a straight line. Near x equal to 3. Near x equal to 3, we keep where is it? We keep x minus 3. Well, we replace x by 3 in other factors. So it's a 2 times 3 plus 1. So it's a 7x minus 3 square. So near x equal to 3, the polynomial is more or less like 7 times x minus 3 squared. It's a parabola, opens up. Okay, so let's summarize everything. Let's summarize it. well, it's a bad graph, possibly. Okay, we have a negative 1/2. We have 3. 3, possibly 3 is here. At a negative 1/2, it's a 49 over 2 times x plus some number. So it's this way. At 3, it's a 7x minus 3 squared. It's like this. And the x-intercept is done. Y-intercept, where is y-intercept? Y-intercept is 9. Let's assume this is 9. And the large number is like the 2x cubed. The behavior theorem tells us it's like 2x cubed. What is 2x cubed? 2x cubed is like this. So when x is very large or negative large, so it's like this and this. And between them, so first of all, you have to cross this up, the line, cross it. And you already have one turning point. From going up to going down, you have another turning point. This one has at most 2 turning points, so there's no other turning point. You have to go down. So this is more or less the graph of the polynomial. Okay? And if you want to make it more perfect, you will add some more sample point. For example, you can evaluate the function at 1, you evaluate the function at 2, you carefully label the values. In the textbook, they did the computation at 1. They got at 1, the value is 12. Let's check. When x is 1, 2 times 1 plus 1, this is a 3, and 1 minus 3 is 2. So it's a 3 times 2 squared, 4, it's 12. Okay, so this value should be 112. So you go up and down here. So there's, well, I don't say this is turning point. I just use this point to help us to go up or go down. I don't know where the turning point is. Okay, this isn't. I never say it's a turning point. I just try to give it a better support. Okay. But there's one turning point between 0 and 3. Here it goes up, and then it will go down. Okay, very good. So this is the analysis of the graph of polynomial functions. And you can see what we did. We had several steps. We have degrees and the behaviors. We have x-intercept, y-intercept. Then from multiplicity, we know the touch across x-axis. And from the degree, we also know the number of the turning points, the possibility. And then we have the behavior near zeros. Okay, the behavior near zeros. Once we finish everything, we are going to just label them. If you feel you don't, you have a too big gap, you evaluate the function at some special point, easy point. I will not ask you to evaluate possibly at the square root of 2 or stuff, because you don't know what is the value at the square root of 2. You will possibly pick up 1, 2, 10, any easy point. Okay, so once you got this, you try to sketch it. In the current moment, if you have some problem like this, the evaluation, the sketch will be simple. We cannot give you some complex function to graph. That one, you don't have enough tools to do that. Okay. Okay. Now let's see another example. The first one, another example. Fx is equal to x squared, x minus 4, x plus 1. Okay, so let's see. Step 1, it has degree 4. X squared, degree 2, degree 1, degree 1. The sum is degree 4. Degree 4, the leading term is x squared times x, x to 4. X to 4 has a graph like this. So and the behavior will tell you at left and right part you will have this type of a graph. Okay, so this is our first part. And step 2, we're going to get x y intercept. Y intercept f0. X equal to 0 is 0. X intercept fx equal to 0. You solve it. Here you get x equal to 0, x equal to 4, x equal to negative 1. This is a multiplicity 2. At 0 you have multiplicity 2. This one has multiplicity 1. Multiplicity 1. Here, degree 1, degree 1. Okay, we got a multiplicity. And 3. This one has a multiplicity 2. The graph touches the x-axis at 0. The graph crosses the x-axis at 1, I'm sorry, not 1, at 4 and negative 1. I look at this 1, but the 0 is 4. Multiplicity is an odd cross, even touch. Okay. And step 4, the degrees of 4, there are at the most 3 turning points. 4 has at most 3 turning points. Okay, and 5 is the behavior near zeros. Okay, so near x equal to 0, near this solution, you keep this x squared because 0 comes from x squared term. And you replace x by 0 in other two factors. So you get negative 4 and 1. So it's negative 4x squared. So near 0, the graph is more or less like negative 4x squared. Near x equal to 4, this term is kept. So you get 4 squared, x minus 4, and times x plus 4 plus 1 is 5. So it's 80 x minus 4, 16 times 5, 80. So it's 80x minus 320. It's a straight line. And near x equal to negative 1, negative 1, yeah. You keep this x plus 1 term. Negative 1 squared is 1. Negative 1 minus 4 is negative 5. So it's more or less negative 5x plus 1 is a negative 5x minus 5. Okay? Okay, so that's the conditions. We have everything. Let's summarize. Let's sketch. Negative 1, 0, 4, 1, 2, 3, 4. That's 4. Negative 1, 0, 1, 2, 3, 4. And the y-intercept is 0. Okay. So near negative 1 is like the graph is like the negative 5x minus 5. Near 0 is negative 4x squared. Negative 4x squared. This is negative 4x squared. Okay, and at close to 4, it's 80x minus 32. 320, so it's like this. And the under behavior is like you hold your two arms. So, and we want to connect them. You see here, you already have one turning point. This place, down, up, you change the direction. So definitely here you have one turning point. And this part, you're going to down, your graph is moving down, and then graph moves up. You have another turning point. 1, 2, 3, 3 turning point at the most. So there's no wave. And then you can just pick up sample point. For example, when x is 1, f1, what is f1? f1 is 1 squared times negative 3 times 2, negative 6. 1, 2, 3, 4, 5, 6. Wow, it's very, very low. And f2, 2 is 4 times negative 2 times 3. Wow, even negative 24. I don't know, it's somewhere. And f3 is 9 times negative 1 times 4. Negative 36. But anyway, don't make a corner, just make it small. Okay, so that's more or less like the graph. So you go down, up a little bit, and down and up forever, for good. Okay, so first, the degree. Degree give you the end behavior and xy intercept, and then you get the touch or cross situation, and then you get the number of the turning point, and you carefully study the behavior near zeros. And once you finish all these informations, you try to label them and try to connect them, and be careful about the number of the turning points. The next example is to use the graphing utility to analyze the graphs. We cannot use graphing utility, so I will skip this. Example, and a cubic function of best fits. So we don't have tables. We cannot use calculator. So let's skip this section. Let's skip this example. Okay, so we finally finished this long section, section 5.1. It's a very, very long section. It has a lot of information, especially the final part, analyze the graph of a polynomial function. Do some exercise, make sure you understand the steps. Okay, so we finish this section, and we are going to move to the next section in the next video, the section 5.2, properties of rational functions. Okay, so we finish this section. We finish this video. Thank you.